Thanks. Thank you, Ellen. That was the best description of all I've heard ever. And it is a safe place. So my name is Jane Hollingsworth. I'm happy to be here. I never attended one of these events. I really didn't know it existed. And then I was asked to speak, and I was told that all these people come to this thing, and I was very curious. And so I'm thrilled to be here to share a little bit of the story. Now, the other instruction I was given here was that I was supposed to bring a demo. Well, we don't do demos. This is life sciences, biology, those sorts of things. So the only demo is me. So that's what you've got. My background is I'm actually not a scientist, but I'm surrounded by scientists, and I'm fascinated by their brilliance and what they can do. So what I try to do is complement that brilliance and bring it to fruition. So I've started a couple of life sciences businesses, which we've taken through with venture capital and IPO and sold them. And so now I'm doing it a little bit differently. And Immunome is one of those companies, and we're running this now. It's a relatively early stage company focused on cancer immunotherapy. And we're running it by getting experts, the best experts we can find, working little bits of their time as consultants on pieces of business. So I think that's a good model. It saves money, gets the best expertise. We also have a group in the lab that really does all the work. Am I getting an echo here? Okay. So this is about immunotherapy. And anybody around here reads the paper, which probably nobody does anymore. I do. It is very hot, and has been very hot. And the reason it's very hot is because the promise is now really starting to come to fruition. Things are happening that has been dreamed about for many, many years. And the potential really, not only in cancer, but for disease in general, to use our immune system to solve some of these problems and cure disease is astronomical. And it's so exciting because there has been some real success in the last few years. And what that has done, other than, of course, help those particular patients, it's brought money to the field. So more investors are interested, which allows companies like Immunome to really grow and develop their little piece of immunotherapy. And so, just basic background so you can understand the technology a little bit better about what we are trying to do and what's different about Immunome is the immune system has cells. And they recognize self, the good stuff, and invaders, the bad stuff. And without that, we could not sustain life. So there are various ways, I won't go into them, that the immune system attacks these invaders. And there's one of these ways that we have latched on to really see if we could make some progress. The lymphatic system is where a lot of is the war zone to a large extent. And so we are using lymph nodes as a source for following the trail the immune system gives us. So, two of the basics, B cells and T cells. B cells are called B cells because of where they come from. They come from the bone marrow, and they've been called B cells for short. Their job is to create antibodies, and antibodies run around and attach themselves to the invaders. T cells are two different kinds of T cells, and T cells you hear a lot about, probably a lot more about than you hear about B cells. T cells, they're helper cells, and they're killer cells. The helper cells are really more of the communicators. They tell antibodies and others where to go. The killer cells are just that. They're the bad guys that go kill, and that guy up there, he's definitely a killer cell. I was really proud of myself, by the way, that I could find this stuff on the internet, copy it, put it into it. I just like a little credit for that. Because the presentation I had and I was playing with, you would have been really boring. So I'm saving you from that. So here's a little flow. It's kind of fuzzy, hard to see. But over there we start with a B cell. And we were working with B cells, so B cells are really important. B cell finds antigens, which is basically what they attach themselves to. They then move along. The helper T cells, the nice T cells, they wait until, the B cells are activated by these helper cells who are, as I said, communicating to the rest of the immune system. Once that happens, the B cells divide. There's a memory cell, which is how when you get sick once, ideally you don't get sick again with the same virus, and the plasma cells. The plasma cells down here are the ones that produce the antibodies, down here at the bottom. And these little things, you see pictures like that, that's the antibody, universal symbol. And once those antibodies are on there are various other pieces here. This is an eater cell. You can see with the teeth, does a good job of that. There's T cells in here following that end up doing the work, the killing. So that's kind of a little bit of a simplistic flow. And we are focused on this. This works for everything. Autoimmune disease, think about that. Infectious disease, HIV, cancer. There's a lot of money that's flowed into cancer for obvious reasons, and now particularly into cancer immunotherapy. So what we are doing is focused on the antibody. The antibody ultimately becomes the drug that ultimately leads to an improvement in the disease or even a cure. And the difference is we are able to use human cells. So over time, as monoclonal antibodies were first used 20, 25 years ago, there was an intense desire to be able to figure out how to use human cells and follow that trail to where they lead and thereby find ideal products to fight disease. The problem was human cells, when you pull them out, and we're pulling them from lymph nodes of cancer patients, early stage breast cancer patients primarily, who appear to be fighting the disease, and when that happens, antibodies are produced. So we pull those antibodies out. But historically what had happened is when you try to use those antibodies, create monoclonals with them, and screen, they will all die within hours typically. So the field used mice, engineered mice cells, humanized them, there are all kinds of things. So the goal of doing human was the key here. So what we've done up above is the traditional discovery process to find a drug. There's all kinds of labs, and in each little box there, you're going to have a whole team of people, a department, if you will, that has to work on this piece of it. And what they do is they have educated guesses as to where the target is, meaning where on the cell you want to go to try to cure disease. But ultimately, it's a little bit of guesswork, shooting to some degree in the dark. And it took years, lots of money, and at the end, you'd have a target, but you still didn't have the antibodies to go with that target. So very imperfect. Here, we're starting with the human system, and we're following that. The reason we can do it is because we figured out, our founders figured out, a technology that allowed the human cells to stay alive and be stabilized for a period, months and years as it's turning out. So we can use those to screen and find new drugs. And this is a little picture of what it is we're doing. You take a biopsy, lymph node typically, from a donor patient. You put those through the process to create the hybridoma with the fusion technology, and then you do a screening process. Does your antibody bind to cancer cells and not normal cells? Because if it binds to normal and cancer, if you put it in there with something toxic, you're going to kill the good with the bad, which is the whole point of the immune therapy, is not to do that. And then you end up with a pair, a target and an antibody together, and they look for each other. So when you have that, you don't have to say, I'm not going to have a target, then I'll run through a whole other process of trying to find an antibody. We now have the team, the lock and the key. And that's what's been really rewarding. And now we're finding very, very, very quickly multiple target antibody pairs, which are the drug products that we will then take forward into the clinic, which is where we are now. So that's my story. Questions?
Can I ask the first question, since I have the mic?
Yes.
Okay. So how do you differ from the personalized therapies that take a piece of the tumor and use that to synthesize DNA to... you explain it better than I can. I just know that exists.
You take a piece of the tumor. I mean, I'm not really sure what your question is, but obviously you take a piece of the tumor and you analyze it, you can look for signs, you can look for antibodies, you can look for all kinds of things that would help you do more than just shoot in the dark and either shorten or improve on any of those processes. But it's completely different than what we're doing now. One, people ask a lot, what about T cells? Because you hear a lot about T cell therapy. Penn, for example, is working on this and having great success, curing cancer in certain people. But what they do, that's individualized, so they take T cells out of patients, they take those T cells and put them through a process of expanding them, engineering them, making them more powerful, more effective, and putting those same T cells back into that same patient. And it's individualized therapy. And that is really taking off and curing people. Mostly in liquid tumors, lymphoma, things like that, not in some solid tumors.
All right, someone with a better articulated question than me.
Thank you so much. I am a 8-year breast cancer survivor who has gone through the chemo and am still on drugs to prevent it. Through the tumor, though, had already gone into my lymph nodes, so I'm reducing that. What does this therapy do with people who have a reduced immunogenicity?
Well, in theory, it doesn't matter. And this is not a therapy per se. This is a way to find effective therapy. So, for example, depending on what you find, you may find something that you combine with another therapy that's quite toxic, for example, and you can use that because you're more directed, because you know exactly where to go, exactly what the target is for that antibody. So one of the ideas behind this is you can really load on the heavy-duty stuff without worrying about killing normal tissue, which is what you do with the toxic treatments like chemo.
Great, thank you.
One more time for one more.
Do you think the way to ultimately beat cancer is going to be in individualized approaches, or do you think we'll ever come to a time when we can find a one-size-fits-all solution?
Neither. It's somewhere in between. What they're working on now with a lot of these individualized approaches definitely has to be personalized, because cancer is not, even breast cancer is many different things. Prostate cancer is different things. So it must be personalized to the type of cancer you have. But what they're working on has some real promise, and I think will bear out someday, is in the individualized T cell work, where they're taking it out of one person, putting it in the same person, that they can create banks that will actually work for more than just that one person, because then they focus on similarities in blood types and things like that. So I think that holds real promise.
Great.
Here.
One more?
All right, one more.
All right, John.
Are there any preventative applications to this technology, or is this only applicable once someone is diagnosed?
Well, again, it's a technology, a way to find treatments. So probably it's just for treatment as opposed to, developing a vaccine or something like that. But good question. I don't know.
All right, great.
Tell me, we have time for one more?
All right. Not the mic, one more, right?
I love you, Brad. Quick question. Where and how are you getting donors? Patients.
That's good. You sound like an investor. We have arrangements with, our guys in the lab have arrangements with a number of different breast cancer centers and hospitals. And so we get patient donations from there, and the patient sign consents, and that's where it comes from. But that took a good bit of time to work out, so if someone wanted to do this tomorrow, that is a hard thing to get into place.
Jane, thank you very much.